I'm not in presentation mode yet. Yes,
Okay.
perfect.
So welcome everyone to this week's Quantum Theories of Fields, Matter and Strings talk. Today we are delighted to have Andrea Antinucci from Oxford University. He will talk about his recent work on defect conformal manifolds. Andrea, thanks a lot for accepting our invitation. It's a great pleasure to have you today, so you can take it away.
And thank to you for inviting me. It's great to give a talk to this nice series of seminars. And yeah, today I want to talk about mostly the second paper here that I wrote with these amazing collaborators, Christian Copetti, that is also here in Oxford, Giovanni Galati, who is in Brussels, and Giovanni Rizzi, who is in Paris. There is some idea that was already in a previous paper, but today we'll mostly focus on this paper here. And as a broad introduction, everybody starts studying quantum field theory, focusing on local operators, particles, mostly if you come from some like high energy background. But importantly, quantum field theory is not only about local operators and particles, and there is much more stuff to be interested in that is there, and there is no reason to not studying it. And for instance, there are extended excitations in the Hilbert space. There are states that don't have finite energy. They have like finite energy for unit length. So they are excited state like springs, or even more extended like domain walls. And similarly, if you want to study quantum field theory in a sort of like Euclidean approach, focusing on operators, there are extended operators that are not supported on point, but are supported on some higher higher dimensional manifolds, at least like one-dimensional manifold. And there are many examples that I will discuss in a second. And clearly there are several relations between these two concepts. Um, for instance, clearly an extended operator acting on the vacuum will create a state that is an extended state. And vice versa, it's often the case that extended operators can be viewed as extended defect can be viewed as word line or word volume of states that are very massive but low energy, and they leave this word volume. The prominent examples like Wilson lines in gauge theory. And on top of this, there are special type of operators that are topological, meaning that these are extended operators that, however, when you insert them in correlation function and you try to vary a bit the support, the correlation function doesn't change. So this is called topological operators. And in the modern language, we regard all of them as symmetries, or maybe better, generalized symmetries, or even maybe better, sometimes we should not even call them symmetries, because these are just like a sort of generalized conservation laws that are not associated to any like presence of a real symmetry in the theory, but still this property of operators being topological, it's a form of a conservation law. And my talk will mostly focus on this class of objects, especially in conformal field theory, so extended defects. But I will use some tool from symmetries and from generalized symmetries. So it's useful to keep in mind that extended operators can have this dual like um, presentation in this story. Okay. Also, please stop me at any time if you have some questions or something is unclear. I will try to make the presentation a bit pedagogical, so feel free to stop me at any time. So just to give you like some example to keep in mind during the presentation of what can an extended defect possibly be, there are roughly speaking two classes of possible way of like introducing an extended defect. One is what we may call a word volume presentation, meaning that you write like operator equal to something, and you have to say what is this something. The simplest example is what many people call a pinning defect, in which you start from some local operator O, and you integrate it over a submanifold of your spacetime. So this is an extended defect that is constructed out of local operators. So it's likely that most of the properties of this extended defect can be inferred from the properties of the local operator. Slightly more interestingly, there are Wilson lines in which you also write operator equal to something, but that something is an integral of a non-gauge invariant object that is, for instance, a gauge connection. And a more general presentation that has like special cases, both of them, is by coupling with extra degrees of freedom living on the word volume. For instance, you have your bulk CFT, and then on a submanifold, you place some other degrees of freedom with its own theory, and then you couple the two with some coupling involving both degrees of freedom living on the defect and some bulk operator. And another type of defect that you can construct, I mean, another way of presenting defect that sometimes can be reduced to the previous one are by imposing certain boundary conditions on some submanifold. And this is very general. And for instance, you have some submanifold, you remove that submanifold from the spacetime, and you modify your part integral by allowing field configuration that are singular in that submanifold, and you impose some boundary condition. And the defect that I want to discuss today are actually some sort of like mixture of these two way of presenting it. But I just wanted to give you like an overview of what kind of object you can keep in mind. So why do we care about defects? For sure, I mean, we should care about them because they are there. So why not to care about them? And moreover, they are very good probes of strong coupling dynamics. So even if somebody want to say, no, I don't want to care about extended defect, I only care about local operators, but there are several properties of quantum field theory that are much better probed if you study the dynamics of defect. Typical examples are Wilson and Tooth lines in gauge theories that can probe, for instance, confinement. And even more generally, there are many properties, even like local properties of quantum field theory, that are very good, like tested and probed if you start studying your CFT in presence of defects, boundary, and all these kind of things. Okay? At least but not last, if you're interested in condensed matter physics or statistical physics, it's often the case that defects are physically realized as impurities in your physical system. For instance, you can model an impurity, namely you have your Hamiltonian in some condensed matter system, and somewhere you put some impurity. This can be often thought as a defect, so some extended operator that is also extending in time. Okay? And so it's a very important question to ask once we understand that these defects are there. What is the space? What are all possible extended defects that we can construct in a given QFT? And this question is a bit ill-defined because if we ask it in this way, the space is obviously huge. Because if you think about this sort of presentation of the defects, I can write any QFT, any coupling, and I will have a different defect. But a much more well-defined question is to ask about universality classes of extended defects. So I can ask, for instance, I can make both the bulk and the defect to flow, and I go in the infrared, and I can ask what are the possible universality classes. And the universality classes are conformal defects in CFT. And we want to understand what are the possible conformal defects that I can define in a certain CFT. A conformal defect, by the way, is an extended defect that preserves the maximal amount of conformal symmetry that is geometrically preserved by the defect. So a p-dimensional defect will preserve the subgroup of the conformal group. Okay? And as I told you, these are very physical objects because they arise in many critical systems as impurities. Good. Any questions so far about this general introduction?
I can ask a question.
Sure.
So if you consider conformal line defects, the relevant group is like SL2R. I'm not able to see how this SOP plus 1, comma 1 is equivalent to that SL2R. Like, is there a group isomorphism?
In that case, it's SO here is SO2, 1,
Mhm.
and SO2, 1 is up to some discrete gauging is SL2R.
Okay, that.
It's probably SL2R mod Z2, yes. Good. So one aspect that I want to discuss today is the main aspect of this talk that has no analog for local operators It's an aspect of extended defects that sometimes they can come in continuous family. So this is really has no analog for local operators. Typically, the space of local operators is a discrete space, while for extended defects, sometimes you can have some adjustable parameter. And why is that the case? You can understand it like in this simple example. I mean, very naively, you can take one extended defect, then you can take one bulk local operator, and you can modify the defect by integrating this bulk local operator with a coupling. And you can hope that this coupling is a true parameter that characterizes the defect. However, if you're a little bit more precise, in general, this is not going to be the case because, as you know, in CFT, when you write any coupling, then you have to normalize your theory, you have to normalize your operator, and this coupling will flow. So you can only have a chance to have a parameter here, a truly continuous parameter, if this operator is marginal on the defect. So if its dimension is the same as the dimensionality of the defect, so then this coupling is dimensionless. But even in that case, most of the time you will not get a continuous family of defect because this parameter will be either marginally relevant or marginally relevant. And it's very hard, even though it's the most interesting case, to have an exactly marginal coupling. So that means that you have some coupling that you added, and there is no normalization of that coupling. It's exactly marginal, and you get what is called a defect conformal manifold. Okay, so you have really a continuous family of defect. For each value of the parameter, you get a continuous. You have a different defect, and this is similar. You have to like compare in your mind with what happened like just with conformal manifold of CFTs that are also very rare, and actually are much more rare. It's very hard to have a CFT and being able to deform it with a continuous parameter, and you have a continuous space of CFTs. This is often the case in supersymmetric cases, but in non-supersymmetric cases, it's very hard. And this question is not so much different with defects, even though it's a little bit better, and I will explain why. And so this conformal manifold, yeah, of course, they are manifolds, and it's interesting also to ask what is the geometry of this manifold, what is the topology, if there is a metric, and if we can predict the existence of this conformal manifold, if we can give like a solid, robust prediction that some coupling is exactly marginal. As I was saying, for defect, the situation is a little bit better than for conformal manifold of CFTs, because whenever you have a continuous global symmetry of the bulk theory that is broken by the defect, you do have a conformal manifold of defects. And the reason that was outlined in this nice series of paper is actually very easy to understand. So when you have a continuous symmetry, let's focus in this simplest example of just a U1 symmetry. So you have a current. So you have this standard word identity, but in presence of the defect, the word identity is modified by a term that is localized on the defect. So you have a delta function on the defect, and this operator that is called the tilt operator, and it's an operator living on the defect. Okay? And just by dimensional counting, you can see that the dimension of this operator is exactly the same dimension as the dimensionality of the defect. But moreover, since this equation is an exact equation, you can argue, and you can also read these papers for like more detailed explanation, that this tilt operator is actually exactly marginal. So when you deform your defect by adding the tilt operator, the corresponding coupling will not be renormalized and will not acquire anomalous dimension, and it's an exactly dimensionless coupling, and you have a family of defects. On top of this, the manifold that this coupling is spanning is a compact manifold. In this case, S1. Actually, this is not, I mean, it's intuitive, but it's not totally obvious, but nevertheless, it's true. Even more generally, if you have a global symmetry G, a continuous global symmetry is broken down to some subgroup, this conformal manifold of defect is the following homogeneous space, just G mod H. Okay? Just to give you a slightly different perspective of why you should expect this to be exactly marginal. This is just pictorial, but so whenever you have a continuous symmetry, you can construct the following topological operator by integrating the current over a codimension one submanifold. And these various defects that are related by activating lambda are obtained from the original defect by wrapping them with the topological operator. So maybe a subset of the topological operator will be just absorbed, and that corresponds to the subgroup H, but others will not be absorbed, and you will get continuous families of defects that are related one from each other by wrapping the original defect with a topological operator. And this perspective is actually useful because it teaches something. So, okay, for sure, this conformal manifold of defects is very interesting. For instance, you can study the Riemannian structure that comes from the homologic of metric. And this Riemannian structure is also related with studying the 4-point function of this tilt operator. So there are many interesting aspects about the geometry of this conformal manifold that you can study. But on the other hand, in a certain sense, quote unquote, these conformal manifolds are sort of trivial, in the sense that each point in a conformal manifold is sort of physically indistinguishable. So many physical properties, like the bulk defect OP that you can study, you can take like bulk operator, push them on top of the defect, and study the OP. They are independent on the point of the conformal manifold. And that's just because essentially these defects are obtained by wrapping with a topological defect. And other aspect, like the G function that is an effective measure of the number of degrees of freedom living on the defect, is constant along this conformal manifold. And also the reflective properties that I will discuss a little bit in the following, that basically tells you what happened when you throw something against the defect, whether it will be reflected or transmitted, how much will be reflected and how much will be transmitted. All these properties are constant along this conformal manifold. And of course, I mean, to tell the difference, you have to move around the manifold. If you go from one point to the other, you will understand, because there is this interesting Riemannian structure, for instance, that you're moving along this manifold. But the physical property are sort of the same for each point of the manifold. And just to draw an analogy, you can think about moduli spaces of vacua in QFT. And roughly speaking, there are two classes of them. Those coming from spontaneous breaking of a global symmetry, and those that don't come from spontaneous breaking of a global symmetry. And in the first case, all vacua are identical. So it's of course very interesting to know that there is spontaneous symmetry breaking, because you have Goldstone bosons and all these kind of things, and you can predict the low energy theory. But if you sit in one vacuum instead of the other, you won't be able to tell the difference. On the other hand, when you have moduli spaces of vacua that are not coming from spontaneous breaking a global symmetry, and this, by the way, as far as we know, can only happen in presence of supersymmetry, because otherwise this degenerate vacua will be lifted. The physics is different at each point. So for instance, there are singular points where you have emergent massless degrees of freedom, and there is a lot of interesting physics going on. And the type of conformal manifold of defect that I will discuss today are more similar to the second type of situation, even though in absence of supersymmetry. Okay. So I want to give you an illustrative example, and we'll come back to this example over and over during the talk to illustrate the main ideas. And the main example is about the easing CFT in 1+1 dimension. And as you know very well, this is like the simplest minimal model and does not have any continuous global symmetry. Okay, the only global symmetries of this series are generated by the so-called topological defect lines, and there are three of them. And one is the trivial line, and there is a Z2 line that was called eta, and the so-called Kramers-Vanier duality line that is a non-invertible line, and they satisfy these future rules. But there is no continuous symmetry. Nevertheless, it is known since almost 30 years that there is in this theory a continuous, there are actually three continuous family of conformal line defects. And I drew this sort of conformal manifold here, and there are many interesting properties to discuss before I go on. First of all, this is made by three intervals, but two of them are joined in this point. And these are intervals, so they are not homogeneous spaces. So this also tells you that this cannot come from the breaking of a continuous symmetry, as I just explained. And they're all obtained starting from the three topological lines, 1, eta, and n, by deforming with the epsilon operator of the Ising CFT. This is an operator of dimension 1. It turns out to be exactly marginal when you add it on the line. So the coupling will not get anomalous dimension, and you generate these conformal manifolds. So there are 3 points here that correspond to topological defects, but all the other points are non-topological, okay? And you already see here that this is strikingly different from the situation I was describing before, because physical properties, like being topological or not being topological, can change along this conformal manifold. So again,
Can I ask a question?
Sure.
So in the previous slides where you were considering the U1 symmetry and then you obtained the conformal modular space of conformal manifolds as S1, you had a invertible symmetry, but in the case of Ising, we have a non-invertible symmetry. Is that the cause of this, non-homogeneity?
So you will see that it's related with that, but it's not exactly that, because here the non-invertible symmetry of the Ising model is not a continuous symmetry. So the origin of having this like more funky conformal manifold is also the presence of a non-invertible symmetry, but it's not this invertible symmetry. Will be another one that I will explain in a second.
Okay.
Okay. And also, one can compute the reflection and transmission coefficients along this conformal manifold, and they vary. And also, you see this little bit funny property that these two intervals, the one coming from deforming 1 and the one coming from deforming eta, are connected in this point pi/2. And we would like to explain all these feature without doing like any complicated and hard computation. We want to understand why this is the case, and this will be useful. In particular, we want to understand why there is the conformal manifold. We want to understand what is the property that is protecting this deformation from like getting anomalous dimension. I mean, in this example, you can explain this in several ways, but the way I will present it will allow me to go much beyond the Ising model and talk about several different generalizations. So that's why I want to explain this in this simplest case. And so let me explain what is the mechanism that produces this conformal manifold. This is probably like maybe the most important slide. There is no formula, but it's just a general principle. And the general principle is the following. So if you want to study conformal defects, or more generally, even conformal interfaces between two different CFTs, something that you can do, and this is very standard, is the so-called folding trick. So there is this general slogan that conformal defects are the same as conformal boundary in the folded theory, meaning that you can fold around the conformal defect and you will get a CFT that is just stacking one CFT on top of the orientation reversal of the other. So these are just two decoupled CFT. I stack them together, and I can study boundary condition of this folded theory. And so conformal boundary condition of the folded theory are in one-to-one correspondence with conformal conformal defects or conformal interfaces here. Okay. However, the observation is that sometimes it can happen that the folded theory has some extra conserved current that was not there in the original theory. Okay. Maybe you shouldn't be so much surprised about it. After all, like the most trivial example of this is just that you start from one real scalar. If you double it, you get one free real scalar. You double it, you get one free complex scalar that has a U1 symmetry, and the U1 symmetry was not there originally. So this is just completely trivial. But what might be a little bit more surprising, as I will explain, is that this phenomenon can happen even in interacting theories. And we dub this phenomenon phantom symmetry, because it's a symmetry that is not there in the problem that we want to study, but you do a trick and you discover that there is a useful symmetry that you can use to understand your problem. Moral, if you want, is sort of similar to the replica symmetry when you do replica trick. So when you want to study some problem that you can face with replica trick, originally there is no SN symmetry, but after you perform the replica trick, nobody told you have to do the replica trick. But if you do it, you discover that there is this new symmetry, and this is very useful for the problem. And this is morally similar, as you will see. So we do this folding trick, and I will explain in a while why and how we can see the emergence of this phantom symmetry. And if this phantom symmetry is broken by the boundary condition, so the boundary condition, if the boundary condition does not preserve the phantom symmetry, then we have a conformal manifold of boundary condition, exactly as I explained before. It's the same mechanism that I explained before for defect applied to boundaries, but not for the theory I wanted to study, but for the folded theory, okay? So you get this conformal manifold of boundary conditions, and upon unfolding, now there is no longer the symmetry because I come back to the original description, so no symmetry, but using this principle that conformal defects are the same as conformal boundaries in the folded theory, I get a conformal manifold of defect from the conformal manifold of boundaries. Okay? Here I drew a little table to like help you in all this concept that I explained in the last slide. And you can also see that like the G function will be constant again, because the G function is sort of an effective measure of the number of degrees of freedom, and is monotonically decreasing along the RG. So when you have conformal manifolds, you don't expect the G function to vary. On the other hand, the reflection coefficient is not even defined in the boundary picture, because you folded the theory, so there is no way of talking about reflection. As you will see, we will not have time to explain the details, but the reflection coefficient will vary along the conformal manifold in these situations. Okay. So
Can I
are
ask
there
a question
questions?
about the previous slide?
Yes.
So I'm a bit confused about the equality sign here. So you say that the left theory does not have the symmetries that the right theory has, but there is some equality sign. In which sense are they equal?
No, sorry. Yes, okay. This is the equality sign. You have to take it with a grain of salt. It's not
Okay.
that these two things are equal. Sorry,
Okay.
I shouldn't have wrote equality. It's like
Okay. Like an arrow or something.
that's right. It's a like
Okay.
double arrow in the sense that the problem of studying conformal defects or conformal interface between two CFTs is the same problem
Mhm.
as studying conformal boundaries of the folded theory.
Okay.
Yeah, it's not equality. Other questions? Okay. If not, let me to demonstrate that this concept that I just introduced of the phantom symmetry is not, I'm not just describing the empty set. Let me show that the previous story that I told you about the Ising model can be understood exactly in this way. Okay, so we'll explain a couple of points of view in the Ising model, and we'll reproduce the previous conformal manifold, and then I will explain how to generalize to other models. So there is a very simple fact that Ising times Ising is the same thing as a compact boson on orbifold branch at radius equal to square root of 2. So just a compactified boson. Phi is equivalent to phi plus 2 pi, and it's a free boson. It has a charge conjugation symmetry and a gay charge conjugation symmetry. Okay, it's a very standard is equal to 1 CFT. And it's well known that this CFT has two continuous non-invertible symmetries. So, and as I already alluded before, this will be the non-invertible symmetries responsible for this conformal manifold. It's not the Cramer's variant duality symmetry of the Ising model, but they are these two symmetries. And why are these two symmetries there? I will explain slightly different viewpoint in a while, but if you want, this is just coming from the standard momentum and winding symmetry of the compact boson, that after you get charge conjugation, you have to combine, instead of taking the exponential, you have to take a cosine. So this is sometimes called also a cosine symmetry, okay? And so you have these two continuous parameters, theta and theta prime. And of course, it's not by chance that I chose to use the same labels that I use for labeling the conformal manifolds, because they will be exactly the same labels. And indeed, the point is that these two symmetries, these two continuous symmetries, that from the point of view that I just described, are two phantom symmetries because they are not there in the Ising model, but they arise in the compact boson. They have a mixed anomaly, so it's impossible to preserve both of them with a boundary condition. This is a completely general fact. When you have a symmetry with a tooth anomaly, you cannot write down a boundary condition that preserves the symmetry. Okay, so at least one of the two symmetries must be broken by any boundary condition. Okay, and as I'm breaking a continuous symmetry, I will get a conformal manifold of boundary condition, and as I just explained, upon unfolding, I will get a conformal manifold of defects. Okay. Now I want to be a little bit more clear about what are the boundary conditions that I'm choosing, so that I can argue that I can reproduce the previous picture, and there will be like funny properties showing up. So for instance, I can start, I have Ising on both sides, and I start with just the identity line. Okay, so I just fold around the identity line, or I can also fold around the Z2 line. And in both cases, I get this free boson with a Dirichlet boundary condition. So Dirichlet means just like phi equals to something. That something will depend on whether I take 1 or eta. It's also a bit complicated to determine exactly which Dirichlet boundary condition is that. I will not enter into the details, but the only thing to notice is that clearly the momentum symmetry that shifts the boson must be broken by the Dirichlet boundary condition, because the Dirichlet boundary condition is fixing the value of the boson, so the momentum symmetry is broken. On the other hand, the winding symmetry is preserved, but there is no problem because the winding symmetry does not have any self-anomaly. Okay, it's enough to break one of the two symmetries. And so if I start from either 1 or eta, I get like a branch of the conformal manifold that will be labeled by this theta. And I can also explain this funny property that I described before, that these two intervals join on one point. And the reason is that the Z2 symmetry of the Ising model, generated by eta, after folding, becomes embedded into this continuous symmetry that is broken by Dirichlet. Okay? So also Z2 symmetry is broken, and this fact alone explains that these two topological lines, 1 and eta, must be in the same connected branch of the conformal manifold. So if I start from either 1 or eta, I start deforming. At some point, I should be able to reach one common point. Now it's a bit more complicated to explain, but if you on the other hand fold around the non-invertible Kramers-Vanni line, what you get is the Neumann boundary, and the Neumann boundary preserves the momentum symmetry but breaks the winding symmetry. I mean, roughly speaking, the reason is just T-duality. When you do T-duality, you map the boson to the dual boson, and you map Dirichlet to Neumann, and so basically everything follows. Okay. So from this thing that I just explained, I can basically I'm basically able to reproduce the whole picture that I just told you. So starting from N, I can fold and I get this conformal manifold that is labeled by the same parameter that is labeling the winding symmetry, and similarly for 1 and eta. And you also understand why this manifold is not an homogeneous space, but is this interval, because it's exactly the fact that the symmetry that is broken, even though it's not a symmetry of the Ising model, but it's a symmetry of the folded theory. It's a non-invertible symmetry. And the space that is labeling this non-invertible symmetry is an orbifold. This is U1 mod Z2. Okay, so this is an interval, and you have these singular points here. The extreme of the intervals are singular, and so they're a bit special. Okay, and as I told you, this picture also explains in one shot why these two intervals, the blue and the green intervals, are connected at one point. And of course, it explains the whole picture why the deformation is protected, because the epsilon operator. I will explain now why is exactly the epsilon operator. But anyway, the deformation that I'm adding to move from the topological point to the non-topological point. Why doesn't it acquire anomalous dimension? Well, the reason is that in the folded picture, it is exactly the tilt operator of a symmetry that was not there in the original description, but arises after the folding. And so its anomalous dimension must be protected. Okay? I didn't explain to you how to get the reflection and transmission coefficient. You can read the paper for more details, because it is a bit technical, but this is one of the most cool facts of the story, that you can actually use this presentation, this way of explaining the existence of this conformal manifold to also calculate exactly how the reflection coefficient evolves as you go around the conformal manifold. Okay? Good. Are there questions? Okay, if not, let me give you a slightly more general perspective of why this can happen in the Ising model. And this will be extremely useful, because you might think, okay, I told you the story in the Ising model, but you're a bit cheating, because I know from the beginning that the Ising model gives, upon folding, a compact boson. So what happened in another theory, which I don't know what happened after folding, can I predict from the beginning that I will get this phantom symmetry? And I want to explain how, suppose that I don't know that Ising times Ising is a compact boson. I want to explain how I can immediately predict that I get this continuous symmetry, and then I will apply this principle to other CFTs. Okay. The idea is very simple. Okay, I already told you that the Ising model has these three topological lines. And now the thing that I want to emphasize is that if we look at the twisted sector of the Z2 line, this eta line, this contains three primary fields: mu, that has the same h and h bar of the sigma operator of the Ising CFT, but will not be important for our story. And then there are two Majorana fermions, one left-moving Majorana fermion and one right-moving Majorana fermion. So these are local but not genuine operators, meaning that they must be attached to this eta line to exist. So they don't exist by their own. And if you take the product of these two Majorana fermions, of course, this eta line, since it's a Z2 line, it's not. Is there a question? No. Okay. So as I was saying, if you take the product of these two Majorana fermions, you get an operator of dimension, one half, and this is just the epsilon operator of the Ising model. And this is a fully local operator because this eta line cancels. Okay. Now let's go to the folding. And again, I supposed to not know that Ising times Ising is a compact boson, but for sure what I know is that when I fold the theory, I must get at least two Z2 symmetries, one from the left Ising model and one from the right Ising model. So I will have two versions of this eta line that I can call eta left and eta right. Each of these lines has its own twisted sectors. So I will have Majorana fermions left and Majorana fermions right from the left, and Majorana fermions left and Majorana fermion right from the right. But I know it's a bit of a confusing terminology, but left and right does not refer to whether the Majorana fermion is left moving or right moving. It refers to whether it comes from the left copy or the right copy of the Ising CFT. Okay. So when you do this folding in the orientation reversal theorem, basically what happens is that each primary exchange what is H and what is H bar. So this psi R here without the bar comes from the psi bar of the other copy of the Ising model. But the important thing to notice here is just that now I have these two eta lines, these two Z2 lines, and they both have in their twisted sector 1/2 comma 0 primary. And similarly, here I have again eta left and eta right. Each of them has a 0, 1/2 primary, and they come from completely decoupled theories. Okay, so I can play this game of combining the two of them. If I take the product of psi left, psi right here, as you see, since these are decoupled theories, I just get an operator of dimension 1, so it's an holomorphic operator, and it's an holomorphic current because it's a 1, alpha operator, so it has spin 1, and this current is non-local because it will be attached to this Z2 line that is obtained as the product of the two Z2 line from left and right. So it's in the folded theory, I have a Z2 times Z2 symmetry. I'm basically focused on the diagonal, and this holomorphic current is a semi-local operator living at the end of this Z2 line. Okay? And similarly, I have an anti-holomorphic current. And then clearly I can construct some indifferences to get like real operators. And this almost gives me a continuous symmetry. But not quite, because to get a topological operator from the current, I should be able to integrate this current on a line. But I don't know what is the concept of integrating a local operator that is also attached to a topological line. What is happening to this topological line when I start integrating this operator? So I have to invent something more funky to write down a topological operator implementing the symmetry, and to really declare victory and to say that I have a continuous symmetry in this theory. Of course, everything that I'm saying in the Ising times Ising is completely trivial because I know that it's the compact boson, but I'm supposing to not know that to apply this principle to other theories. And here the idea to construct the topological operator is the following. I can take the following topological line that I'm calling A, that is just the direct sum of the identity line plus eta left, eta right. And by obvious reason, my dashed red line here can terminate topologically on this A line, just because the fusion of the two is A again, right? Because A left to right is a Z2 line. And I can construct this configuration. Now my semi-local current is living at the end of this line, but this line is ending on this blue line here. Now, as everything is topological here, except from clearly the local operator, I can push this blue line on the left here. Okay, here I'm doing the opposite, but anyway, what I get is this now local operator J on the A line. Okay, and this is free to move. And now, why this is not a local operator of the bulk, it becomes local on the line. Okay, and as it's local on the line, I'm allowed to integrate it on the line. So I'm not allowed to integrate this operator in the bulk, but I'm allowed to integrate it over this blue line A. And the result of this operation is exactly these two topological lines that I was talking about before. And they become non-invertible exactly because the integral of this current is done on this A line that is a non-simple line obtained as a sum of topological lines. Okay, you can show that this construction gives exactly the same result of these cosines that I was talking about before. Essentially, you can view the cosine that is the sum of the two exponential precisely as this sum that I'm performing here. Okay. Good. Now, this principle can be generalized to other CFT. How do I do that? I will be a little bit schematic. There are many details to fill, so please feel free to ask if you have some objection, because there are many objections to put here, because there are many things that I'm putting under the carpet. But so you can start from two different CFTs in general, and you can start looking at twisted sectors of topological lines. Okay, let me emphasize this point that maybe it can be confusing. Here, I'm using these discrete symmetries to find these operators and to find at the end a continuous global symmetry. But the continuous global symmetry is not necessarily related with these discrete symmetries. So these discrete symmetries are just like a tool to find these twisted sectors. Of course, you might ask, well, why cannot I just look for operators that are fully local and they don't live at the end of line? Of course you can, but you will just find trivial examples. There's only one example, that is the CFT of a single Majorana fermion. Sorry, yes, the CFT of a single Majorana fermion. And in that case, the symmetry will be invertible and you will find local operators. In all other examples, you must look for operators living in twisted sectors. So these discrete symmetries are just a tool to find the continuous global symmetry that I need to discuss this conformal manifold. Now, I start looking for these twisted sector operators at the end of these lines. And suppose that I find one operator psi1 of the CFT1 and one operator psi2 of the CFT2, whose conformal weights satisfy these two equations. So the sum of H1 and H2 bar is 1, while H1 bar and H2 are vanishing. Then, following the construction that I just told you, I get this phantom current in the folded theory. Because when I take the orientation reversal of the CFT2, psi2 becomes this psi2 bar, whose weights are now H2 bar, 0. And when I take the product, I'm just taking like the product of two operators living in different CFTs, so we'll just sum the weights, and I will get an holomorphic current that is living at the end of this line that is obtained by fusing eta1 and eta2. Okay? Now, I'm not specifying whether eta1 and eta2 are Z2, are higher order lines, or if they are invertible, non-invertible, anomalous, non-anomalous. So there are conditions for which you can repeat the construction that I told you before. But just for simplicity and for the sake of the example that we will discuss, you can think that eta1 and eta2 are just Z2 lines, and they can have anomalies, but eta1 times eta2 in the folded theory must be non-anomalous. For a very simple reason, that the twisted sector of an anomalous line cannot be an holomorphic current. Okay? But eta1 and eta2 singularly can perfectly be anomalous, and that will be like actually the interesting case. So apart from all these subtleties, from this construction and from the construction that I told you before about integrating this current over this topological line, I will get some continuous non-invertible symmetries. They will be non-invertible because this current is non-local of the folded theory. And this will be my phantom symmetry that I can use to predict the existence of this conformal manifold of interfaces between the CFT1 and the CFT2. Okay? Because the phantom symmetry is basically always broken somehow. And what we can call the phantom tilt is obtained from the same two primary operators, but now in the parent theory. So instead of looking at the folding, because I can ask, what is the corresponding deformation that I have to add to my defect to describe this conformal manifold? And this operator is constructed in this very simple way. So as you see, it comes from the product of two operators living on the two sides. So it's an operator that only lives on the defect in general, okay? Unless the two CFTs are the same. And it's an operator, is not an holomorphic operator, but it's an operator of dimension 1, and its dimension turns out to be exactly protected in the original theory by symmetry that is not there in the original theory. So the symmetry that is protecting the anomalous dimension of this operator, it's a symmetry that is only manifest after folding. And adding this operator will generate for me this conformal manifold of defects that typically, except from the trivial case of the Majorana fermion, it's an orbifold because it comes from a non-invertible symmetry. Okay? I want to emphasize this other point that in the sort of ordinary case where you just get defect conformal manifold from broken continuous symmetry of your theorem, you can never start from a trivial or even like topological defects, because as I told you, the physical properties will be the same around the conformal manifold. So if one point is topological, all the other points will be topological. So to describe some interesting conformal manifold, you need to start already from some interesting conformal manifold. While in our construction, we can start from a totally boring defect that might be the identity defect or some topological defect, and we can get some interesting conformal defect, but just by this construction. Okay. Now, just to like flash a couple of other examples, you can start looking at these sort of examples in rational CFTs. You can start from just looking at interfaces between WCW model, SUN level K, varies with different N and Ks. And for simplicity, let's just focus on the case in which these eta lines that I was discussing are Z2 symmetries. There is no very important reason to focus on this, it's just for simplicity, but you can easily argue that this is the only case that is going to give you phantom current with abelian current algebra. The reason is easy. It's very easy to explain. It's actually that if you look at the current algebra, if you look at the OP of the current, a U1 current algebra has 1 appearing in the right-hand side. So you have JJ equal to 1 plus something. So these currents can only be attached to Z2 line because it must be some line that squares 1. So if you look for more general examples, and you can look at them in the paper, in which these lines are not Z2 lines, you will get non-abelian phantom symmetries. For instance, you can get SU2 and stuff like that. So you will see the details in the paper, but it's much more involved. And now I just want to focus on the simplest example of just abelian current algebra and Z2 lines. And so by scanning these models, you can realize that these phantom symmetries can only exist if these rank and level satisfy this equation. So there are a finite number of them. And here is the whole list of possible conformal defects of conformal interfaces between SUN level Ks, WCW models. Okay. You can go a little bit more generally and ask for more general WCW models. And this gives me the opportunity of explaining some facts. So when you focus on Z2 lines, there are spin selection rules that tells you basically that the spin, namely the difference between H and H bar of the local operators living in the twisted sector, is constrained by this formula. And here alpha is the anomaly of the Z2 symmetry that can either be 0 or 1. So the possible spins that you can get are integer multiples of a quarter. Moreover, if you remember here, we needed that at least one of the two weights must be 0, meaning that here saying that the spin must be an integer multiple at a quarter means that H and H bar must be also quarter. So to get an holomorphic current, there are actually 3 possibilities. Either they are both 1/2, or one is 1/4 and the other is 3/4, and you can choose the order. And then you can scan all possible WCW models with some gauge group and some level. And this is the whole list of example that you can find. So you can combine 2 of them in which there are weights that sum to 1, and you will get conformal defects and conformal interfaces with a continuous parameter. Okay. So let me conclude by mentioning some extension to higher dimensions and some future direction. So I already discussed co-dimension 1 interfaces in 2D CFTs, but you can ask whether the same phenomenon can exist in dimension greater than 2. And there are a bunch of examples in free theories, clearly. It's like the very simple generalization of what I told you about one real scalar that when you double becomes a complex scalar. You can start from any number of real scalar or any number of fermions, and you can discuss example like this. But of course, this is not so interesting because we are discussing conformal interfaces in free theory, so it's something that we can do also by hand. It is not necessary to go with all this machinery. So it will be much more interesting to find interacting examples. However, there is a sort of no-go theorem for finding interacting examples in IRD. This is a bit sad, but it's not necessarily so sad. So, because this no-go theorem works basically as follows. If you try to construct a conserved current, so a conserved spin 1 primary operator of your CFT of your folded CFT out of primary operators of the single factor CFTs, it turns out that if you look at the unitary bounds, there is no way of constructing them in dimension greater than 2. I mean, of course, the unitary bounds also apply to 2D, but the thing in 2D is that the spin in 2D is not necessarily an integer or an alpha integer. The spin can take any value, and for this reason, you are able to construct these examples. But if you, strictly speaking, apply the unitary bounds in IRD, it seems that there is no example, no analog example in IRD, at least for conformal interfaces. However, honestly, there might be way out to this no-go theorem, because, for instance, you can try to construct gauge invariant primary operators out of non-gauge invariant operators that are not required to satisfy unitary bounds. So we didn't explore this possibility so much, but it would be very interesting to find examples of this conformal manifold of interfaces or defects in higher dimensional theories. And you can also ask for higher codimension objects. So I only focus on interfaces, but you can ask, for instance, whether this mechanism can also allow us to study to predict the existence of a conformal manifold of line defects in three-dimensional CFTs. This would be really great. I mean, here there is no, strictly speaking, there is no no-go theorem, but we have to refine a bit the principle that we use, because the story will be a little bit different in the sense that when you study higher codimension defect, then you're not going to do the folding trick anymore, but what you're going to do is basically you will reduce around the sphere around the defect, and you will go to something like ADS space times a sphere that is the round sphere around the defect. Then you want to get rid of the Kaluza-Klein modes of this sphere, and you may want to, maybe you want to predict whether the resulting theory will have an emergent continuous symmetry. And it's not clear to me how to do that, but that would be like an interesting future direction to pursue. And well, other future direction, for sure, an immediate extension that is immediately doable with a little bit of computational power is to study generalization of the example we discussed, where the discrete symmetry lines we started with are not only non-zeta lines, but are even like non-invertible lines. And in rational CFTs, in general, I mean, even in minimal models, there are a lot of non-invertible lines. So I expect that there will be a plethora of examples that one can study. We didn't do that, but I'm sure that this is something that can be done. And I think it's also interesting to look at the example in coset CFTs or in coset of WSW models. Also because sometimes they arise as the infrared of two-dimensional QCD. So you can ask whether these conformal manifolds that arise in the infrared of two-dimensional QCD has some interpretation along the RG, there are many questions that you can ask that I think are very interesting. And finally, you can ask whether there might be interpretation of the story in holography. For instance, in ADS3 CFT2, you can ask whether there is an interpretation of this phantom symmetry in terms of a bulk theory. And yeah, that's all. Thanks a lot.
Okay, thanks for this very nice talk. Are there any questions?
Is it possible to ask one question?
Yeah, sure.
Sure.
Thanks for the talk. You mentioned the higher dimensional case.
Yeah.
So let's say in massless QED in 4 dimensions,
Mhm.
there is the ABJ non-invertible symmetry,
Yeah.
which is nearly continuous, let's say, right?
Yeah.
Uh, and a related fact is that if you look at Hooft lines that you mentioned at the beginning, they seem to have a continuous parameter. When you define the boundary conditions carefully, like you said, you define the magnetic flux around the Hooft line, but you also have to define the boundary conditions for the fermions near the magnetic monopole. And that introduces a continuous parameter, which is also called theta confusingly. It has nothing to do with the bulk theta, as far as I'm concerned. So can it be interpreted as a tilt operator of a non-invertible symmetry in higher dimensions, or
But
that's too far-fetched?
okay, thanks for the question. But I remember that you last year that this parameter seems to be a continuous parameter, but actually it's likely that it will flow, it will reach a fixed point. So it is not clear that there is a really a continuous parameter, right?
Well, nobody ever computed its beta function fully. I tried to compute its beta function by throwing away lots of diagrams at one loop, and I only like kept one loop diagram. And
Okay,
I
so it's
don't
not
think
really
anybody actually computed the full one loop beta function, to be honest.
okay, but okay, good. Actually, this is really one of the possibilities in the sense that when I was mentioning this way of possibly evading this no-go theorem, this is really one of the possibilities using this current that don't look gauge invariant, but then you can actually construct a topological operator out of that. Other examples are also if you look at abelian gauge theories with non-compact groups. So you can have something like SL2R symmetries that are not associated to any gauge invariant current. So these are examples that maybe can work. So I think there is room for exploring these things in an example like this.
Okay, thank you.
Thank you.
Any other question? Maybe I can ask one. So I didn't quite follow, but you were considering this two SU and WZW models, and then you were folding, and you said you were getting some non-abelian symmetries, right? Are these symmetries non-invertible or
Sorry, which case are you talking about?
yeah, this diagram. Yeah, when you fold this.
No, in this case, you don't get a non-abelian symmetry. I was saying
Ah,
that, so in these cases, these examples that we explored are only with Z2 lines. And I was
hmm,
saying that we focused on Z2 lines just because we wanted to focus on the simplest case where the current algebra is a U1 current algebra. But I was saying that
I
if you
see.
if you focus on more general lines that are not Z2, then you're forced to get a non-abelian current algebra.
I see. Okay.
Okay.
Because
There are
I was going to ask, like, if you have some non-invertible symmetry that is associated to, say, a non-abelian fusion category or whatever,
Mhm.
how can you gauge that? And when you gauge, what kind of degrees of freedom you will get?
So good. Um, when we start, so are you talking about the discrete non-invertible symmetry I start
No,
with,
like
or ah,
continuous.
okay, continuous?
Yeah.
Yeah, I mean for sure. I think you can get some orbifold of some continuous group.
Hmm.
And yeah, there are examples like this. Yeah.
But are you talking about the flat gauging or dynamical gauging? Because in the flat gauging, you don't get any local degrees of freedom in any case.
Sorry, which gauging are you talking about?
Like, let's say we have some non-invertible symmetry associated to some continuous structure, and it's
Yes.
non-abelian.
Yes.
So when we try to gauge this in a non-flat way, like we introduce some local degrees of freedom,
I
what
don't
kind
know.
of okay.
I don't know how to do that. Yes.
Okay.
I mean, yeah. As far as I know, it is not known how to gauge symmetries in a truly concrete way unless you have a local current.
I see. Yeah. Yeah, okay.
I'm not saying it's impossible, it's just that it is not known.
Yeah, I see why it would be a problem. You have to couple the current first to the partition function then.
Right. I
see.
mean, it's not known what is the meaning of coupling these symmetries to non-flat backgrounds. So when people talk about symmetries in terms of topological operators, this is just like one part of the story, because it's the full part when you talk about discrete symmetries. But when you talk about continuous symmetries, there is much more than topological operator. Because continuous symmetries are something that you are supposed to couple also to non-flat background fields.
I see, yeah. Any other question from the audience? Okay. Then maybe let me stop the recording. So if anyone wants to ask